Respected chairpersons, distinguished guests, esteemed researchers, and valued attendees, I appreciate the opportunity to review my findings today. I am Sivaranjani, Ph.D. candidate from KM College under BHARATHIAR University. My Ph.D. specialization is in computer science, and my topic is a survey on leveraging convolutional neural networks for predicting urban microclimates, enhancing urban climate forecasting. Urbanization is reshaping our planet. With over 4.5 billion people, more than half of the global population now living in cities. This rapid urban expansion has profound implications for local climates such as urban heat island and other factors. For instance, during a 2021 heat wave in New York City, localized urban microclimate variations led to a 6 degrees Celsius difference between the downtown core and nearby suburbs, intensifying energy demands and health risks. These challenges underscore the need for precise and reliable urban microclimate forecasting as a critical tool for sustainable urban planning and climate adaptation. The presentation is organized as follows. In this presentation, I will examine how CNNs are being applied to urban microclimate forecasting. Specifically, I will provide an overview of CNNs and their unique strengths in modeling urban microclimates. Analyze key challenges such as data availability, computational demands, and generalization to diverse urban contexts. Propose future research directions aimed at improving prediction accuracy and practical implementation. An urban microclimate refers to localized climate conditions in cities, influenced by factors like buildings, roads, and human activities. With rapid urbanization and climate change, predicting urban microclimates is crucial for managing urban heat islands, improving energy efficiency, reducing health risks, and enabling sustainable urban planning to mitigate environmental impacts. A convolutional neural network is a deep learning model and a powerful tool for improving spatial and temporal data analysis. CNNs can analyze environmental data to predict urban microclimates, enhancing weather forecasting and addressing climate impacts in rapidly urbanizing areas. Let us now take a look at the literature to see how researchers have approached urban microclimate prediction and the role of CNNs in environmental studies. Recent studies have applied CNNs to urban microclimate tasks, including temperature and humidity prediction, heat island detection, and air quality forecasting. Some research uses satellite imagery to predict temperature gradients, while others focus on IoT sensor data. However, a key challenge is generalizing models across cities with varying environmental conditions. Many studies focus on isolated factors with a limited integration of multiple variables. Additionally, there is a lack of comprehensive standardized datasets for training CNN models. As we have already seen, that CNNs are deep learning models designed to handle spatial data. Its key architectures such as 2D CNNs, 3D CNNs, ResNet, and UNet are used to model urban climate patterns. With hybrid approaches, integrating CNNs with the RNNs or LSTMs to address both spatial and temporal dependencies. Key applications include urban heat island detection using thermal imagery, air quality prediction through atmospheric data integration, and improved rainfall and temperature forecasting using meteorological data. Real world examples, including smart city projects, demonstrate the effectiveness of CNNs in urban microclimate forecasting. The accuracy of CNNs depends on high quality datasets and robust methodologies. Next, we explore the key datasets and techniques used to train and evaluate these models. Commonly used datasets such as remote sensing data from Sentinel, moderate resolution imaging spectroradiometer, that is MODIS, and Landsat for temperature and vegetation analysis, weather weather station records for historical meteorological data, geographic information system and urban layout data for climate impact studies, and IoT sensor data for real timing monitoring of temperature, humidity, and air quality. As we have already seen the list of key architectures in the overview of CNNs, the 2D and 3D CNNs are used for spatial and spatiotemporal analysis, whereas hybrid models such as recurrent neural network with CNN or a long short term memory with CNN are for dynamic patterns, and multimodal data fusion is to integrate satellite, IoT, and meteorological data. Data preprocessing enhances data quality, transfer learning tackles data scarcity, and explainable AI, sorry, and explainable AI improves model interpretability for urban planning. Despite advancements, challenges like data scarcity, model generalization across cities, and the need for explainable AI hinder the widespread adoption of CNN based models, highlighting key research gaps for scalable solutions. Challenges include limited availability of high resolution, multimodal datasets, difficulties in generalizing models due to geographic and environmental differences, and the high computational cost of processing large scale urban data. Additionally, most studies focus on isolated microclimatic factors with insufficient integration of variables like wind patterns, vegetations, and urban morphology. The following section delves into promising future directions to overcome these challenges and advance the field. Hybrid models combining CNNs with other machine learning techniques can improve robustness, while standardized datasets integrating satellite and IO data will accelerate research. Additionally, developing lightweight, real time CNN models for edge devices is crucial for urban microclimate prediction. The following section will summarize the key conclusions and outline the broader implications for future research. This paper reviewed the use of CNNs in urban microclimate prediction, highlighting their potential to improve spatial and temporal accuracy. Challenges like dataset limitations, model generalization, and computational costs persist. Future research should focus on hybrid models, better datasets, and real time explainable predictions to support urban climate resilience and planning. Finally, these are the key references that I have utilized in preparing this survey paper. I would like to extend my sincere gratitude to the authors whose work has greatly contributed to this research. I would also like to extend my sincere thanks to the esteemed dignitaries and organizers for this opportunity. Thank you all for your attention.